So imagine it's 1999. An emergency response team gets dispatched to rescue a family stranded by rising floodwaters.
Right. Incredibly high-stakes situation.
Exactly. And they're handed the exact mathematically correct coordinates of the distress call. But when they arrive at the spot, there's just no one there.
Wow. Just empty water?
Just empty water.
Mm.
They were actually searching hundreds of feet away from where the actual victims were holding on.
That is terrifying.
It really is.
Yeah.
And the reason why? Because the map the rescue team used to navigate was anchored to a completely different mathematical model of the Earth than the GPS unit that recorded the initial distress call.
Ah, yeah. The classic datum mismatch.
Exactly. So welcome to today's deep dive. We are tackling the conceptual foundations of Earth geometry, datums, and map projections.
It's a massive topic.
It is. But our singular mission today is to make sure you are fully prepped to ace Section 103 of the GISP exam.
Which is arguably, the most critical section for any aspiring geographic information systems professional.
For sure.
Understanding this foundational architecture, like how we model the Earth, it isn't just about passing a test. It's really about ensuring the spatial data you produce in your career reflects physical reality.
So you don't end up sending a rescue team to the wrong side of a flooded river.
Exactly.
So we've compiled a stack of essential sources for you today. We're pulling directly from standard GIS study guides, geodetic textbook excerpts, and some expert geotech review modules.
There's a lot of dense material in there.
Very dense. But the overarching theme you really need to internalize for Section 103 is that mapping the Earth accurately requires abandoning the idea of a perfect sphere.
Yes, you have to let that go.
Right. Like, we all learn in kindergarten that the Earth is a round globe, but you have to embrace a planet that is actually lumpy, squished, and highly dynamic.
Well, let's start right there with the actual shape of the Earth.
Okay, let's do it.
If we want to assign a coordinate to a physical location, we first have to define the canvas we're working on, right? For the GISP exam, there are 3 primary models of Earth geometry that you must be able to differentiate.
And those are the sphere, the ellipsoid, and the geoid.
Correct. The sphere is obviously the most basic, a perfectly 3D round shape with a constant radius everywhere.
But in professional GIS, a purely spherical model is rarely used for high-precision analysis, right?
Yeah, almost never. I mean, it's computationally lightweight, so it gets used for very simplified, small-scale web globe rendering.
Places where speed is prioritized over actual geodetic accuracy.
Exactly. But if we're calculating geodetic coordinates for a real project, that baseline spherical model just isn't going to cut it.
Because the Earth isn't perfectly round.
Right. We have to account for the Earth's rotation and the resulting centrifugal force.
Which basically spins the planet so fast that it bulges out in the middle.
Yeah, that rotation causes the physical mass of the planet to bulge at the equator and then flatten out at the poles.
The sources actually give a specific number for this. The Earth is roughly 13 miles wider across the equator than it is from pole to pole.
Which is a significant difference when you're trying to map things precisely. And that introduces the second model you need to know for the test, which is the oblate spheroid.
Also commonly referred to as the reference ellipsoid, right?
Yes, exactly. This is a mathematically defined, smoothed-out surface using 2 distinct radii.
So there's a semi-major axis, which represents that equatorial bulge you mentioned,
Right.
and a semi-minor axis for the polar flattening.
That's it. It basically acts as a highly accurate mathematical idealization. It gives us a clean, predictable frame of reference for all our complex geodetic calculations.
Okay, let's unpack this with a visual for everyone listening. If the sphere is a perfect billiard ball, the reference ellipsoid is, I don't know, more like an M&M candy.
That's a great way to picture it.
Just slightly compressed at the top and bottom.
Yeah, the M&M analogy works perfectly conceptually. But for the exam, you need to imagine that candy shell as a rigid, unyielding mathematical boundary.
Got it. But even that idealized ellipsoid doesn't capture the actual messy physical reality of the planet, does it?
No, it doesn't. And that's where the third model comes in, the geoid.
Right. The lumpy potato.
The lumpy potato.
Mm-hmm.
The geoid is the true physical shape of the Earth based entirely on gravity.
So how does that actually work? The sources mention it was first defined by Carl Friedrich Gauss back in 1828.
Yes. The geoid basically represents mean sea level, but more specifically, in physics terms, it is an equipotential surface.
Equipotential meaning equal gravity everywhere.
Exactly. It represents the shape the surface of the global oceans would take under the influence of just Earth's gravity and rotation alone.
So we're completely ignoring winds, tides, ocean currents.
Right, ignoring all of that, just gravity. Every single point on the geoid experiences the exact same geopotential pull.
I want to focus on the mechanics of that for a second, because the internal mass of the Earth is, well, entirely uneven.
Very uneven.
We have dense tectonic plates, we have deep ocean trenches, massive mountain ranges. So the gravitational field can't be uniform.
Oh, the variation is extreme. Compared to that smooth mathematical ellipsoid we talked about, the geoid deviates significantly.
Do you have an example?
Sure. Think about Iceland. There's a huge amount of dense volcanic mass there, which increases the local gravitational pull.
Because more mass equals more gravity.
Right. So in Iceland, the geoid actually bulges about 85 meters above the mathematical ellipsoid.
Wow, 85 meters.
Yeah. And conversely, if you look at southern India, there is a massive mass deficit deep underground, causing the geoid to actually drop 106 meters below the ellipsoid.
That is wild. But wait, if the geoid is entirely dependent on mapping these minute fluctuations in gravity all over the world, how are we actually measuring that accurately?
That is a great question.
Because I know historically, surveyors use plumb bobs, like
Yeah.
just suspending a weight on a string to find the local direction of gravity, and they use ground-based gravimeters.
Right, and those worked for local areas. But mapping the entire planet's equipotential surface, that requires a totally different approach.
Let me guess. We had to go to space.
We had to go to space, specifically using the GRACE satellites.
GRACE, which stands for Gravity Recovery and Climate Experiment, right?
That's the one.
Yeah.
And they're really fascinating. They operate as a pair, orbiting the Earth in the exact same path, separated by about 137 miles.
Okay, so one is just chasing the other.
Exactly. But the key to their measurement isn't taking pictures of the ground. It's a highly precise microwave ranging system that constantly measures the exact distance between the two satellites down to the micron.
Wait, really? A micron?
A single micron. So imagine the lead satellite is approaching an area with a denser mass, say the Himalayas.
Okay, huge mountains, lots of mass.
Right. The stronger gravitational pull of that mountain range physically accelerates the lead satellite.
Just a tiny bit.
Yes, that sudden, minute acceleration pulls the first satellite slightly further away from the trailing satellite.
Oh, I see. And the microwave ranging system records that tiny increase in distance.
Exactly. Then, just moments later, the trailing satellite passes over that same Himalayan mass, gets pulled forward itself, and the gap closes back up.
That is genius. By continuously tracking those microscopic changes in the distance between them, scientists can just reverse engineer the exact gravitational anomalies down below.
And that is exactly how we map the Earth's lumpy equipotential surface today.
Okay, I see the logic there. But here is the friction, and I think this gets into our next exam topic.
The heights.
Yeah. If we now have two completely different models, the mathematical reference ellipsoid and this physical gravity-based geoid, we immediately run into a measurement problem.
A huge problem.
Right, because when a surveyor says something is 100 feet high, we now have to ask, high relative to what?
And that is a massive exam-critical topic.
Okay.
If you are going to model elevation in GIS, you absolutely must understand the four distinct types of heights.
Okay, let's break them down for the listener. First up is orthometric height. I'm assuming this is what most people casually think of as just true elevation, right?
Right.
Because it's measured relative to the geoid.
Correct. When a topographical map lists a mountain peak at, say, 10,000 feet, it is referencing orthometric height based on mean sea level.
But if you walk up that same mountain with a raw GPS receiver,
It will not give you the orthometric height.
because a raw GNSS reading gives you the second type of height, which is ellipsoidal height.
Exactly. As the name implies, this is strictly the height above the mathematical idealized reference ellipsoid. It completely ignores the localized gravity field or sea level.
Which means we need a way to reconcile the two.
We do.
If I have a raw GPS reading, but I need my topographical map to reflect physical mean sea level, I have to bridge that mathematical gap somehow.
And that bridge is the third height you need to know, geoidal height, which is frequently called geoidal separation.
So geoidal height is the distance mathematically calculated between the ellipsoid and the geoid at any given point on Earth.
That's it exactly.
For everyone listening, if you want a reliable strategy to lock this in for the GISP exam, just frame geoidal height in your mind as the gap between math and reality.
Oh, I like that. That is a perfect mental hook.
The gap between math and reality.
And keep in mind for the test that geoidal height can be expressed as a positive or a negative number.
Oh, right, going back to the Iceland and India examples.
Right. If the physical geoid bulges above the reference ellipsoid, like in Iceland, the geoidal height is positive. But if the geoid dips below the ellipsoid, like the gravity deficit in India, the number is negative.
Got it. Okay, there's a fourth height mentioned in the study materials, which is dynamic height.
Yes, dynamic height.
It seems a bit more abstract, to be honest. The sources say 2 points with the exact same dynamic height might actually be different physical distances from the geoid.
Yeah, it throws people off. Dynamic height is purely a measure of the equipotential surface itself.
Right.
Because the gravity field bends and warps based on underground mass, water will only flow between 2 points if they have different dynamic heights, regardless of what their orthometric heights are.
So it's really about gravity, not tape measure distance.
Exactly. It's highly specialized. It's mostly used for large-scale hydrological modeling, like managing water levels across the Great Lakes.
Okay, that makes sense. So let's pivot slightly. If I'm out in the field at a known coordinate and I need to walk 200 feet at a 45-degree azimuth, I need a mathematical way to figure out the exact coordinates of my destination using these models,
Right. You are describing the first geodetic problem.
sometimes called the direct problem.
Yes. You are given a known starting point, an azimuth, and a distance, and the mathematical challenge is calculating the exact coordinates of the destination.
And I assume the second geodetic problem, or the inverse problem, just works backward.
Precisely. In the inverse problem, you are given the exact coordinates of point A and point B, and you must calculate the azimuth and the distance between them.
Okay, so we have the shape of the Earth defined, we have the logic for calculating elevations, and we know how to measure distance across the curve.
Right.
But if I'm dropping a pin on a digital map, that coordinate system has to be physically anchored to the crust of the Earth somehow.
And this is where we bring in datums.
Datums.
A datum is essentially the mathematical model that pins your coordinate system to the physical Earth. In geospatial technology, a datum provides your frame of reference.
For the exam, there are specific horizontal datums you're expected to differentiate, starting with the two major North American ones.
Right. NAD27 and NAD83.
Let's start with NAD27.
So NAD27, the North American datum of 1927, is what we call a localized datum.
Meaning it's anchored to a specific spot.
Exactly. Surveyors essentially took the Clark 1866 ellipsoid, which was the best mathematical model they had at the time, and they physically anchored it to a survey station at Meads Ranch in Kansas.
Okay, wait. Stop right there. Why base an entire continental grid on a random ranch in Kansas?
I know, it sounds arbitrary today, right? But before satellites, regional surveyors used optical triangulation.
Like literally looking through instruments from hilltop to hilltop.
Exactly. They needed a physical starting point roughly in the center of the contiguous United States. So they aligned the mathematical ellipsoid so its surface perfectly matched the physical geoid right at that specific spot in Kansas. And from there, they triangulated outward.
But mathematically, if you force the edge of the ellipsoid to perfectly touch the crust in Kansas, aren't you essentially pushing the center of that ellipsoid away from the actual center of the Earth's mass?
Yes, that is exactly the problem. It was highly accurate for North America, but completely useless for Europe.
Because it's completely skewed off-center.
Right. Historically, there were hundreds of these disconnected, localized datums all over the world.
Sounds like a nightmare for global mapping.
It was. But as technology advanced, particularly with the advent of global navigation satellite systems, or GNSS, a locally anchored datum just wasn't sufficient anymore.
We needed a geocentric datum.
Exactly. One that anchors the mathematical model to the exact center of the Earth's mass.
And that necessity birthed NAD83.
The North American datum of 1983. It uses a much more accurate ellipsoid called GRS-80, and its origin point is the center of the Earth, not a ranch in Kansas.
And there's also WGS-84 mentioned in the sources.
The World Geodetic System of 1984. It is the default for modern GPS and is functionally very similar to NAD-83, though. They have drifted apart slightly over time due to tectonic plate movement.
We also have vertical datums to contend with, right? To establish where zero elevation physically exists.
Yeah, and the critical one for the exam is NAVD-88.
The North American vertical datum of 1988.
Right, which establishes zero elevation based on a specific tide gauge reading at Father Point in Quebec, Canada.
Okay, so the study guides place a massive emphasis on datum transformations.
As they should.
If you take a data set mapped in NAD27 and overlay it onto a map using NAD83 without mathematically transforming it, The coordinates don't physically move on the screen, but their real-world location shifts dramatically.
Because the underlying mathematical anchor has moved. A point can shift by tens to hundreds of feet.
Which brings us right back to that emergency response scenario at the beginning.
Exactly. If property lines, flood control maps, or dispatch systems have mismatched datums, your spatial analysis is fundamentally broken.
And even a perfectly geocentric datum from 1983 isn't static, right? I mean, tectonic plates move, California shifts a few inches a year.
They do. And that dynamic reality is pushing the GIS industry toward epoch-based or time-stamped datums.
Meaning?
In the near future, coordinates will require an X, Y, Z, and a time variable, acknowledging the physical drift of the Earth's crust since the datum was established.
That is fascinating. So we have our 3D model pinned down.
Yeah.
But GIS software mostly operates on a 2D monitor.
Right. The real world is 3D. Our screens are 2D.
We have to flatten the Earth, which means we have to break the math.
Yes. Going from a 3D geocentric model to a 2D plane requires a map projection. And it is physically impossible to flatten a sphere without introducing mathematical distortion.
Think about an inflatable globe, right? If you cut it in half and try to force that plastic completely flat on a table, you just can't do it.
No, it won't lay flat.
You inevitably have to stretch the plastic in some places, or tear it.
And managing that stretching or tearing is the entire science of map projections.
Okay, so for the exam, there is an acronym you need to remember, SADD, spelled with 2 Ds.
Right, SADD. This helps you understand what properties get distorted.
Shape, area, distance, direction.
No single flat map can perfectly preserve all four simultaneously. You always have to compromise.
To project the 3D data, cartographers use what are called developable surfaces. Basically, they conceptually wrap a geometric shape around the globe.
And the three main surfaces you must know are planes, cylinders, and cones.
Got it.
How that surface intersects with the globe dictates exactly where the distortion occurs.
Okay, break that down for us.
Well, if the mathematical surface merely touches the edge of the globe at one single point or along one specific line, it's called tangent.
Tangent.
Right. At that exact point or line of contact, the scale factor is exactly 1.0. There is zero distortion.
But if you mathematically slice the globe, like the developable surface cuts through the 3D shape, that's a second projection.
Yes. A second projection will intersect the globe at two distinct lines. Along both of those second lines, the distortion is zero.
But as you move further away from those lines,
The distortion aggressively increases.
okay, there is a fantastic rule of thumb in the study guides for which surface preserves which property.
It's very helpful for the test.
So, cylindrical projections are generally best for preserving direction. Conic projections are used for preserving area and distance, especially for mid-latitude regions stretching east to west like the United States.
Right.
And planar, or azimuthal projections, are best for polar regions.
Exactly. We really need to look closely at why cylindrical projections preserve direction, because it explains a highly tested projection, UTM.
Universal Transverse Mercator.
Right. On a physical globe, lines of longitude converge at the poles. They all meet at the top and bottom.
Right.
But if you wrap a cylinder around the equator and project those lines outward onto it, you mathematically force those converging longitudes to become perfectly parallel lines.
Okay, and by making them parallel, any straight line you draw on the map becomes a constant compass bearing, or a rhumb line.
Exactly. It perfectly preserves direction for navigation. You can just draw a line and follow your compass.
But to make those lines parallel, you have to stretch the landmasses horizontally as you move north or south away from the equator.
Which introduces massive area distortion at the poles.
So how does UTM solve that?
Well, a standard Mercator wraps the cylinder around the equator. A transverse Mercator rotates that cylinder 90 degrees and wraps it around the poles.
Oh, interesting.
This allows cartographers to slice the Earth into manageable vertical strips. UTM divides the Earth into 60 distinct zones, with each zone being exactly 6 degrees of longitude wide.
I see. By keeping the zones incredibly narrow, the distortion at the edges of the zone remains minimal.
Exactly. Inside each specific zone, you can measure in real meters with a high degree of confidence.
But UTM employs a very specific mathematical trick that you absolutely have to know for the exam.
The false easting.
Yes. The central meridian, which is the exact middle longitude line of each zone, is assigned a false easting of 500,000 meters.
Right.
Why not just call the middle 0?
If the central meridian was 0, any location to the west of it would have a negative coordinate.
Ah, and computers don't like that.
No, they don't. By assigning the center a value of 500,000, moving west simply drops the number to 400,000 or 300,000. It prevents spatial analysis software from crashing due to negative integers.
It keeps all the geocomputation positive and clean.
Precisely. But knowing which projection to use isn't just an academic exercise to pass Section 103.
Right, it has real-world consequences.
Relying on the default projections in modern mapping software can entirely ruin a project, which brings us to the trap of Web Mercator.
Web Mercator. It is the default projection for almost all major online map providers, right?
Yes, and it's utilized for web mapping because it is conformable, meaning it preserves local shapes and angles.
So if you zoom in on a city block in Web Mercator, the right angles of the streets look like perfect squares.
Exactly, it looks visually correct at a street level.
But the sacrifice is area, and the distortion is so severe as you move away from the equator that the Department of Defense explicitly bans the use of Web Mercator for any official spatial analysis or area calculations.
That's right. The visual distortion is why Greenland appears larger than the entire continent of Africa on most online maps, even though Africa is roughly 14 times larger in physical reality.
14 times larger. The study sources provide a startling mathematical example of this. If you measure a long-distance route on a Mercator projection using the software's flat measure tool, you might get a result of 3,124 miles.
But if you take that exact same real-world space and measure it on an Albers equal area projection, which utilizes a conic developable surface to accurately preserve scale over that region, the true measurement is over 24,000 miles.
It's just staggering. Because a projected coordinate system isn't using decimal degrees like a globe, it's measuring flat space in actual meters and feet. If the mathematical flattening stretches the landmass, your digital ruler stretches right along with it.
This is perhaps the most crucial takeaway for your entire career. Modern GIS software is incredibly powerful, but it will trick you.
How so?
When you load datasets with different datums or projections, the software will often execute a projection on the fly, so the layers visually line up on your screen.
But a visual alignment on a monitor is not a mathematical datum transformation.
Exactly. The software might make the map look seamless, but the underlying data matrices are still sitting in two totally different geodetic realities.
So if you run a spatial analysis tool, like, say, calculating the total acreage of a forest fire, or determining if a chemical spill is within 500 feet of a water reservoir, and your datasets are not mathematically transformed into a unified datum and appropriate projection,
the software will confidently hand you a completely wrong answer.
you must manually verify and transform all your data into a single, appropriate geodetic framework before executing any analysis.
That step right there separates the mere software operators from the true GIS professionals.
Okay, let's run through a rapid-fire summary of your Section 103 study checklist.
Let's do it.
You need to know the difference between the physical, gravity-based geoid and the mathematical reference ellipsoid.
Right.
You have mastered the 4 types of heights, specifically recognizing geodal separation as the mathematical gap between the ellipsoid and the equipotential surface.
The gap between math and reality.
Yes. You understand why surveying transitioned from the localized, optically triangulated NAD-27 to the geocentric, satellite-based NAD-83.
Leaving the Kansas ranch behind.
Exactly. You know the S80 distortion shape, area, distance, direction?
Right.
And you know the mathematical mechanics behind developable surfaces, tangent lines, and the 60 zones of UTM.
If you can articulate those mechanics, you have the conceptual foundation completely locked down.
Beyond just passing this exam, mastering this architecture is a heavy professional responsibility. When aircraft navigate through low-visibility mountain passes, or when a city engineering department draws its 100-year sled maps, they're relying on your ability to ensure the data on the screen rigorously reflects the actual physical reality of the Earth.
It's critical infrastructure, and as a final thought to ponder as you continue studying, the Earth is not starving.
Right.
Tectonic plates are continually drifting, subsidence is altering ground levels, and climate change is actively redefining mean sea level.
So that equipotential surface is changing.
Exactly. Our physical reality is constantly shifting beneath our feet. We are rapidly approaching a future where static coordinates will become completely obsolete, forcing the entire industry to adapt to 4-dimensional time-stamped datums.
Wow.
The map of the future will be a living, breathing variable.
A living map. Best of luck on Section 1 and 3, and we will catch you on the next deep dive.